Yeah, perfect. So the next speakers that we have right now is Jessy, Grizzle, and Ghaffari. So first of all, I would ask whichever of you is going to share the screen to start sharing it right away. So Jessy, Grizzle is a full professor at the Control Systems Lab in the University of Michigan. He's the director of the Michigan Robotics. And Mani is an assistant professor as well in Michigan, and he just started a new lab there. Both of them are going to be talking about navigation and mapping using the Cassie robot and also the MIT Cheetah. So please, the floor is yours.
Okay, now I am unmuted. So thank you, everyone. I'm really pleased to be here with Mani Ghaffari. I think you're used to me mostly talking about feedback control of blind bipedal robots, but with the addition of Mani's expertise, we're doing a lot of work now on robots that have a pretty advanced perception system. In fact, so the stuff we'll be talking about today is focused on the Cassie bipedal robot and the MIT mini-Cheetah, but it should work for all of the robots in this view. So the Cassie robot, what we've done to it is built a custom torso. We essentially 2 years ago turned Cassie into a digit robot by Agility Robotics before digit was actually built. So we've got a 32 beam Velodyne LiDAR, RGB-D camera, some extra computing power, a battery to run it. So that added about 11 kilograms to the robot, and then Cassie alone with her battery is around 33 kilograms. So I'm going to play a video in a second. If I hit the optimize button, we'll see if that works out well. But let me explain a little bit about what's going to be happening. So as the camera images come into the robot, on the right, what you see is that there's a neural network that is breaking up the camera image, assigning semantic labels to the pixels in the image. We have a really good method for fusing the LiDAR and camera data. So when that comes in, we actually can then build a colored 3D semantic map, because we can associate the LiDAR positions by fusing them with the camera image into a full 3D map. And so then we, in the lower left-hand corner, you see that we have a safety system, because unfortunately, you know, with this custom torso, if it falls, it breaks, there's no protection. And that's certainly one of the big advantages of Agility's new digit robot, is that everything is integrated and much more safe. So the map here is being built in real time. The planner was a very simple D-star planner, and then the robot was told to, at every intersection, take a left turn. It comes back. The loop closure is done by pure odometry here, and in the future iterations, it'll be full real-time SLAM. Now, what we wanted to do is to get this working in a much more robust environment. So one of the first things we had to do was get the feedback controller improved. So my student Yukai Gong presented Tuesday on his new feedback controller, which allows Cassie to walk up and down all the valleys on the Michigan Wayfield instead of just walking around on the sidewalk. It can also go up and down the humps. I will, well, I think what I've seen is we can run over as much as we want. So maybe I'll keep going here and let you see Cassie going through the humps. And so this is under teleoperation. So now, can we do anything similar to this in fully autonomous mode? So This is at night, so we're not using the camera. It's 100% LiDAR. Just as Sung Bae showed, the LiDAR image is being converted into an elevation map. Cassie is using that. There's an RRT star planner with an anytime replanner that's using well, it's a real time. It's an anytime reactive planner based on a control Lyapunov function. So if the robot deviates, it has essentially vector fields that guide it back onto the desired path. The controller here is not taking advantage of the height information. It's only the planner here that's using the elevation information. You can see the students using our human gantry, and that's once again because if the robot falls, it breaks the perception system. You can see the path that is being planned. You can see the humps showing up very well in the elevation map, and Cassie can make it through in the dark, and it's all looking extremely good. So what we'll be doing soon is bringing Cassie through that with this extra weight on her at over a meter per second, and then going up and down the large humps. So it takes a lot of system integration to get something like this working, and the fact that our students got it going is really amazing. So there's very good state information that we have presented on at other times. There's the very nice fusion of the camera and LiDAR data, which is then with image segmentation and fusion giving us that 3D semantic point cloud that you saw. It then builds a map. An occupancy map is then used for the cost function. There's a goal finder, as I mentioned, RRT star, control the Lyapunov function, and then that goes down to our low-level controller. So, Mani, would you like to take it from here?
Yeah, thank you. What about night vision with Jessy?
Yeah, night vision goggles would be cool, wouldn't it? That's
next.
That's next.
So all my videos are during the day. I don't have anything at night. So I'm going to talk about our latest work on mapping, because just building a rich map, semantic map that the robot can understand what's going on, that's just has been the main challenge of robotics mapping historically. With deep learning, we have a lot of options now. The work that in particular is very exciting, our latest work, is multitask learning, multi-layer Bayesian mapping framework. This is a work done by our PhD student Lu Gan and Youngji Kim from KAIST. She was visiting us. Next, please. So typically, when you want to build a map, you collect sensor data, get a trajectory somehow using a state estimation, and then build a geometric map. It might have color to show you the appearance. But in the next slide, you will see that now that we have deep learning, we can have a reasoning block that will give us a high-level measurements. These are in form of semantic labels that we can assign a category to each object or pixel in the image, or pointed at 3D. This is supervised because this is a human understanding of the environment. It makes sense to have whatever number of classes that we want to teach robots to know about the environment. So this part is supervised, but there are also, as I show later, is that, next slide, please. We want to do multitasking because it's not just scene segmentation. The robot needs to know at the very least traversability, no-go and go zone at the very least. And potentially we can build on different tasks such as affordance, for example. One thing that we want to work on is that what is the utility of each point in the environment for the robot? Different vehicles will have different understanding. So these will be robot specific, and they can take exoceptive and proprioceptive signals combined to do representational learning and scene understanding to provide measurements that are not possible to get with a typical sensor directly. Now, the network that you see, it's for multitasking is like that. And the way we do the self-supervised, yeah, I guess I can say more word, Jessy.
No, it's fine. Sorry if I'm messing you up on the sequencing, Monty. So what about friction? I need friction. I need to be able to know what my ground reaction force limits are, Monty.
Yeah, ICRA is very excited about friction, and I know a lot of people worked on it, but I think we are at a good point now with this framework to build a friction layer for specific robots by accumulating experience. One reason we use deep learning, because we want to improve the model as we collect more data. It's not possible with traditional machine learning. The multitasking is also good because we can share information and combine everything. Of course, in practice, it doesn't work always as expected. So we use attention mechanism to make it work. And that's, there are a lot of details there. But in this work, our self-supervised traversability labeling has this pipeline. We collect sensor data. We get the trajectory using the SLAM or odometry. We build elevation map, convert it into traversability map, and then we project it onto the image. This way, we have a time coherent measurements. Future scenes are projected into the image with the correct timestamp. This will be noisy. So we have the semantic segmentation. We know particular classes are traversable for a particular vehicle. Then we collapse the semantic labels in traversability and non-traversable, and then filter the image. We get the final clean ground truth traversability, and then we can do self-supervised training. So on top of that, once we get the measurement, we have a closed form Bayesian inference for each layer. Now, each layer, not only we have inference for that, they also semantic posterior will serve as prior or extra measurement for the other layer. So we sharing information during inference as well. This is a very efficient framework in terms of reusing information. We use conjugate distributions. The prior is a conjugate, has conjugacy with the likelihood. The posterior is the same form. It's very efficient to implement. The inference is done in logarithmic time complexity.
So how come, Monty, how come you don't want to just do everything with a neural network end to end?
Right, my philosophy is that neural network is doing signal processing with me. The inference, there should be a map inference module sitting on top of that. It is not good to use the measurements directly because single frame is noisy. Even if neural network is using multi-frame for prediction, that is still noisy. I need an inference to get the posterior by accumulating data as long as I want. This is a spatial smoothing. I can accumulate observations forever. And every time it gets better, statistically speaking.
Exactly. Thank you.
Thanks for asking that. You're the perception expert now. I need to learn control. So this is open source. Multitask learning is available online. The mapping is available. There will be a paper on arXiv soon. If you want to run it on your data, feel free to reach out to Lou or us. And next, I'm going to talk about, this is an example of a map. Maybe we can show this a little bit.
It's going.
Yeah, on the left, you see the semantic map. On the right is the traversability map. And maybe we can fast forward it a little. And this is basically the same field that Jessy was talking about, control and autonomy, and then the robot can build this map as well. So next, I'm going to talk about mini-Cheetah. We got it last year. We added a custom sensor suite. We have a GPU, and we moved the robot into the forest. In the next video, we show our last Saturday data collection. This is a typical forest on Michigan campus. You see the robot view, the depth. There are a lot of dead woods and leaves. Some plants are tall. They can block the camera.
So is the robot under teleoperation here though, right?
Yes, yes. It's, we haven't transferred autonomy on the robot. We collect data and process it offline for now because we have limited resources on the robot.
Coming soon.
Yeah, so in the next slide, I'm going to motivate why we are going to do that reckoning the way we do. This is state-of-the-art feature-based SLAM. Orbit SLAM is the robot is moving, entering the forest from the road. Suddenly, the SLAM system fails because there's a perceptually degraded situation. So the next slide shows why this happened. This next please. Now this is the reason it failed. It doesn't look too bad, but the plant is tall, the illumination and all of that. So this can be for a while, and then just single IMU is not going to fix that, even though single frame may be okay. But so that motivates us to having a proprioceptive tracking state estimator. It won't fail until the hardware fails. So the next work, we show some results on that. The vanity clip that we had on Cassie, it's all good, but mini-Cheetah doesn't have contact sensor. That's very important to bound the IMU drift. So to estimate contact, we use a convolutional neural network to get combined IMU and encoder data. Again, because we want to accumulate data as we collect more data on different ground types, it should get better over time. So then next slide, you will see sample results in the lab on polished concrete inside the laboratory.
Yeah, I just want to add that Cassie sometimes has struggles if we start taking large steps on that polished concrete. It's very slippery.
Yeah, so there are a lot of weak regularities, and this convolutional network can figure it out. And it is a relatively, it turns out it's not a hard problem to, basically we're learning a piecewise linear function to model contact data, contact events as a classification problem. So then I'm going to show you some more results in this. Next one is, so we have data sets, we're going to release it currently in 2 ground types. There will be more. Next slide, please. So this is on concrete indoor data set. We generate ground truth contact, we run the InvaniKIF, then we use the step estimated contact with a neural network, almost identical result. We use Orbit SLAM, it works well here as a proxy to ground truth. The next one is outdoor in MR setup. We have outdoor motion capture system here on North Campus. Similarly good results. So this is very good. Now we're making a lighter version of the network that we can export it on Jetson and run it online on the robot. So that is what we're working on. That's all I have to say, and I pass it on to you, Jessy.
Yeah, so our next steps is, we're going to integrate all of these systems that Mani's talking about onto Cassie as well. I think the contact estimation work his student has done is really outstanding. As Mani said, we've got lots and lots of different terrain that's within about 10 minutes of the new Ford Motor Company robotics building. It's a great opportunity. We just want to thank our sponsors, Toyota Research Institute and NSF. And then most of all, we just want to really thank the fantastic graduate students in our lab. So with that, we'll stop.
Thank you, Jessy and Mani. I like the fact that you guys are asking each other during the presentation, so that's cool. Yeah, I just have a quick question about that. The last thing that you were mentioning, that you're planning to integrate these strategies also on Cassie. I wanted to actually know how hard is it to have a strategy or an algorithm that you can integrate in different platforms, but these platforms are not quadrupedal. One is bipedal, one is bipedal, and the other one is a quadruped. So how hard is it to integrate that, and what are the challenges? So what do people that are working on these 2 platforms need to do to have a better integration for navigation and mapping algorithms?
Well, Mani will help me, but I think that it's the part of it is the modularity of our approach. The real low-level stuff is all implemented at 2 kilohertz, but then you have other operations that are integrated in a ROS environment. And so it's pretty straightforward for us to take on the second computer on Cassie and run the various invariant EKF, the image segmentation, the fusion with the LiDAR data. So it doesn't matter what the legged platform is, as long as it has adequate computation. And then the really great contact work that Monty's lab has, we think that'll be much improved. If you see the middle pic, much improved over what we're using on Cassie now, because if you see the middle picture on Cassie I have here, the black bars at the bottom are springs, and we are currently detecting contacts by the compression of the springs, but the neural net is able to use more than just what's going on at one joint to do the contact detection. So we just view it as, whether it's 4 legs or 2 legs. I mean, fundamentally, you're really concerned about what's happening on one leg at a time, and we're taking that information and then integrating it at the higher level via ROS. Monty, you want to add anything?
Yeah, just to quickly add that we have sufficient level of abstraction to transfer it. We do see this problem as an embodied problem, but that doesn't mean it's specific to just one platform. There is a little work to transfer it to a different robot, but there's a sufficient, again, level of abstraction to transfer it easily to other platforms. And the sinking foot here is a challenge because the spring is good if the ground is firm. Now the leg is sinking, which we will add covariance estimation for contact and other measurements to adjust these height drift that we get from the reckoning and sinking grounds, soft grounds. So this data-driven approach will really enable all our previous model-based work to flourish in real world.
Cool, thank you for your answers. Perhaps we can take one also question from YouTube. Russell is asking, for detecting contacts, how do you define contact? For example, how do you consider slipping where the foot is in contact with the ground, but not zero velocity with respect to the ground? And also, like for example, for me also on soft terrain, is it when you first start touching the terrain itself, or when you start having a sufficient force to detect the contact?
Yeah, so what's being done on Cassie currently is when we get sufficient weight transfer, and that's what's being done with the spring. With the neural net, the cool thing is we can do some human labeling with the motion capture systems that we have available of data. But then we can also run tons and tons of these experiments and start doing self-labeling and optimizing the definition of contact in various terrains. So sort of like that pile of chips you see to the left of the middle picture, the mud. We don't want to have to go into terrain and then tune what we use for the spring deflection. So this is where I think Monty's team.
The labels are automatically generated, like Jessy said, but we make sure they're correct. The moment there's a contact with the physical world, that's contact, right? We don't care about the force necessarily for generating data. That is up to the network to figure out the force behavior based on the IMU input, and maybe if you have force input or model. So that is quite simple. The reason we need to be careful is that because we need to collect more data in different ground types to make sure we have enough diversity of environments to correct that. And it's interesting that we think the neural network is now doing better than the ground truth. That's when we look at data, we're conservative in generating the labels, but neural network can detect all of them, even challenging ones.
Yeah, it's really hard to walk in pea gravel, for example, because you're essentially slipping all the time. And so I think there's lots more terrain that we can take on as Monty and I combine our various skills in robust feedback control perception mapping, deep learning, self-labeling. It's really an exciting time here at Michigan. And what I can see, it's an exciting time everywhere in the world in this area. It's a very competitive. We feel a lot of pressure from you guys. I hope you feel a little bit from us, but I think everybody's under a lot of pressure to produce great work. And it's really, really fun to be here today with you all, share what we are doing.
Yeah, exactly. It's a really cool moment for our research field, definitely. Thank you so much for your presentation and for your questions. There are other questions on YouTube and on that we also copy through Zoom. We'd be really happy if you can answer it. And then with that being said, I'll give the chair back to actually that's Dimitrios now, so that he can introduce the next speaker.
Thank you.
Great, thanks so